Did you have anything in particular you wanted to talk about?
Um, my daughter had a question. And she was sitting here the other day, and I didn't ask you, and it kind of felt like a jerk. Um, but can I ask you that?
Of course.
Okay. She said iodine is in the column of chlorine,
Yeah,
but don't you put iodine in water to be able to drink it?
you do. Yep. True statement.
If it's killing the germs, how come it's not hurting you when you drink it?
Because there's lots and lots of cells in your body.
Okay.
And when the germ cell dies, it's just dead. Mostly it's because you're waiting long enough for it to do its job. So the dosing is incredibly important. That way the iodine that you place in the water kills the stuff that's in the water and reacts with other things in the water, and it turns from iodine, which is toxic, to iodide, which is not.
Ah,
So
iodine to
I2
iodine.
ends up turning into two iodides.
Oh, right. Mhm.
So, do you know what a goiter is?
Uh, isn't it like a mass?
That's a problem with your thyroid because of a
Okay.
lack of iodine, and you end up having a fairly substantial sized mass on your neck. And we don't really have it in Western culture anymore because this is table salt, and most of the table salt sold in the United States is called iodized, which means
Right.
they substitute some I's in for the CLs, and then your thyroid's happy.
Oh, very interesting. Here, I'll have to look that up. Iodine. Well, she won't feel so ignored now, thanks.
Sure.
Um, yeah, so what I um does it always take um is energy always heat, and does it always take heat to break apart, or no, to break apart molecules?
No, you definitely don't need heat to break apart a molecule. Um, so the atmosphere, so when a plant undergoes photosynthesis, it takes carbon dioxide out of the atmosphere and water out of the ground and turns it into sugar and oxygen. And there's no heat there. It uses the energy from the sunlight to break those chemical bonds.
But the energy from the sunlight isn't heat, it's radiation.
Energy comes in lots of forms. Light is a form, heat is a form. So yeah, it comes in different forms. I don't know what else to tell you.
Comes in different forms. And does it always come from the sun?
No, it could come from nuclear
Decomposition.
reactions. It could come from uh, yeah, pretty much for the most part, it comes from the sun. Like all the energy on the planet can at some point be traced back to the sun, with the exception of a few things like like nuclear energy. But if I'm talking about chemical energy and not nuclear energy, the planet has been sitting around for so darn long, and it was just a rock at first, and now all the energy that is stored on the planet is stored on the planet because it came initially from the sun.
Okay. And then it's stored in these things.
Plants, people, oil,
Right.
coal.
Sort of like batteries. So then the anthracite that is more combustible, not is it combustible or it's just more powerful because there's less oxygen?
Um, we talked about fire a couple of lectures ago, and do you remember what you needed?
No, carbon and oxygen.
No, you don't need carbon.
Carbon. Good to know. No, I just know oxygen.
There's we talked about like they come in third grade or something, the fire department talks to you, and you need oxygen and fuel and heat.
Okay.
So you have some object, and then you take oxygen, and it combusts, and then I get X with O's on it. That thing has been burnt, and that thing no longer can be burnt. All right. So if I
What do you mean
attach,
I get X with O's on it?
yeah, so whatever this object is over here, this could be anything. It could be anthracite, it could be hydrogen, it could be iron. If I take this thing and I react with oxygen and I get another thing over here, that's this thing plus oxygen, this thing is burnt now. So when I start off with something that has oxygen already attached to it, I can't burn it because that's what burning means, that I attach oxygen to it. So if it already has oxygen attached to it, then I can't attach the oxygen that's already there. So that part can't burn. So if I'm talking about like, well, I'll just make easy numbers here. C100, H250, and O40, then 40 oxygens have already been attached to this stuff. If I get rid of these oxygens, then there's more places for me to put oxygen. So if I have 40 oxygens already on this molecule, that means there's only 60 carbons left to burn. The other ones have basically already been burnt. Do you know what another term for burning is, for combustion is?
Oxidation.
So if something has an oxygen on it, that means it's been oxidized.
Okay.
And so if I've already got 40 oxygens in this coal, then 40 of them have already been oxidized. That means I only have 60 left to oxidize or 60 left to burn. So if the less oxygen that's in the coal, the more combustible it's going to be. Does that make sense?
Yes.
So something simple, if I just take iron and oxygen, I can put them together and make Fe2O3. So two things could happen here. I could either allow this reaction to happen slowly, and then we would probably refer, if this reaction happens slow, we would call this whole reaction rusting.
Uh-huh.
Or and then I could have the same exact reaction that produces the exact same products, and if this reaction happens fast, we would call this burning. So rusting metal and burning metal, they end up with the same products and produce the same thing. If I burn this metal, I actually end up with a whole bunch of heat. A triangle on the in a reaction means excess heat, and this also produces excess heat. Do you know those small hand warmers that look like they feel like they have a coffee filter with some powder in the middle?
Hot hands.
Hot hands, yeah.
Mm-hmm.
This is hot hands. So they're sealed, packaged. The coffee filter paper inside of it has very finely ground iron. And when you crack it open, then the oxygen in the air gets through the little coffee filter paper stuff to the iron and actually makes rust, which is why when you crack one of those hot hands open after they've been used, it looks like rust because it's rust. But then they also produce heat. So if it happens slowly, then I get a little bit of heat over a long period of time. If it happens fast, then I get a whole bunch of heat all at the same time, and it's kind of can be kind of ugly. Burning metal can be kind of ugly as far as its
What
controllability.
about water speeds the process of rusting? Is that the oxygen in the water?
So
Or am I misunderstanding
no, you're fine. Just a
the
second.
process?
Just a second.
Mhm.
Okay, so if I've got iron, I need to get the oxygen onto it. And if I have oxygen that's in its aqueous state, so that means so I've got water molecules, sorry, water molecules, and the water molecules can be attracted to oxygens. And so this is in its liquid state, and if there are water molecules around the oxygen, then that's in its aqueous state. So the water will have O2 in it. We're not talking about this oxygen that's in water that's doing the rusting. If you put pure water on metal, nothing will happen. Okay?
Okay.
Because the oxygen is already happy being combined with the hydrogens. But the water that ends up, like rain and whatnot, you did that first lab, right?
Yeah,
So rain is not pure, correct?
right.
So there's stuff in rain, and that stuff you'll end up having electrolytes like sodiums and chlorides, and then there's oxygen, and that makes the process happen faster. So if there's electrolytes in the solution, then this reaction can occur more quickly. Which, if it's just out in the rain, you're going to have that kind of stuff in the water.
Sure. Okay. Electrolytes. Okay.
So if you dumped Gatorade on a nail as opposed to just regular water, the nail would react a lot. It would rust a lot more quickly.
Okay. Cool. Um, and then this whole sort of mm, 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 energy change.
What page are you on?
I am on 77.
137?
77.
You're on page 77.
177.
177. One. Okay. So we talked a little bit about this last time. When I have a chemical reaction that occurs, let's see. Let me put this thing back up.
I think I get this, but there's just a lot of stuff going on. I want to make sure it's fitting in right.
Well, okay, so we're just going to burn some water molecules or burn hydrogen and make water molecules. So what I actually need are so this is up here, this is the way you would write the reaction, but it's a little harder to see. So what I did is I just took everything and laid it out. So this 2 here means 2 of this thing here. So that's why I have 2 H2s. That's called the coefficient. So if I want this hydrogen right here to turn into a water molecule, what do I have to do before that happens? I have to break this chemical bond. That bond right there needs to break. I also need to break both of these bonds. Okay? If I break both of these bonds and this bond, that leaves me with an H and an H and two O's. And this O attacks both of those hydrogens and it turns into a water molecule. But
Mhm.
initially, what did I have to do? I had to break these bonds, and that takes a little bit of energy. So we talked about this last week. When you burn a piece of paper, you initially ignite the paper, and what's happening is I'm breaking those bonds. But once those bonds are broken, then they reform and they make this bond and this bond when I'm doing this water molecule. And when you make bonds, you get lots of energy out of it, or you get energy out of it. And in this case, you get lots of energy. So some of this energy that was made is used to break the bonds on the next set of hydrogens and oxygens. So the reaction can continue and go on its own pace. So just like with a piece of paper and burning it with a match, you don't need to keep the match on the paper the whole time. Once the
Mhm.
paper starts on fire, then it produces enough heat to burn the next set of molecules. And so it steals a little bit of its own energy to keep the reaction going.
Okay. So then what I'm hearing is what you need here is your initial, you just need enough energy to start that process and
Yep.
then you get
You need
what?
enough energy to get the reaction going. And then once it's
Right.
going, it can keep itself going.
Okay. And what do you call that when it's keeping itself going?
A spontaneous reaction.
Okay.
A non-spontaneous reaction forces you to put energy in all the time, or the reaction stops. So a spontaneous reaction, a good example for that would be this is cellular respiration. So this is what we're doing right now. And
Mm-hmm.
if you lock yourself in a closet or go into a room and turn all the lights off, this reaction still happens because this is a spontaneous reaction. The opposite reaction, so what's the opposite of cellular respiration?
I don't know.
Photosynthesis.
Okay.
So what happens if you take a plant and put it into a closet and close the door?
It dies.
It can't do photosynthesis anymore, so it dies.
Mm-hmm.
So one of these is spontaneous and one of these is non-spontaneous. This one is non-spontaneous because this is photosynthesis and requires constant energy input. And this one is spontaneous because it just happens. Glucose with
Okay.
oxygen produces carbon dioxide and water with no energy input.
Mm. How poetic. All right.
Yeah, circle of life, a little bit of Lion
Right.
King. The plants can't live without us. We can't live without the plants.
Mm-hmm. Yeah. What do you think about all these people getting cremated? Do you think that's a waste of energy?
Um, what else are you going to do with them? Because I think burying them in a cemetery is a terrible idea.
Really?
Takes up too much space.
Like dogs.
Doesn't matter.
It doesn't matter. They're
Doesn't. I
gonna
mean,
turn into carpet either way.
unless you're just gonna bury them haphazardly in the woods, that would be fine. Or dump them at sea, that would be fine.
Yeah, that was more what I meant.
Yeah, those would be, I don't know, more.
Would it be productive?
Absolutely, you just turn into soil
Right.
or food for sure.
Right.
But as long as you're not burying them in a cemetery, I'm pretty much fine with whatever it is you want to
You mean like all packed full of chemicals and in a big plastic box?
do. Yeah, I hadn't thought about that, but yeah, Yeah, no mummifying anybody. Bad idea.
Mhm.
Environmentally speaking, that is.
Right.
I mean, just drop them in a hole and put a baby tree on top of it.
They do that in Goldendale.
Oh,
There is a
is it a cemetery forest kind of thing?
uh, it's a natural burial cemetery
Oh,
where you can essentially, choose um
plant,
your
tree,
burial vessel if you want one, something that's
cardboard box.
compostable and get plucked in the ground. Um, okay, so then there's the exothermic and endothermic energy.
That this another way to say spontaneous would be
Uh-huh.
exothermic, and non-spontaneous would be endothermic. So these basically mean the same thing: spontaneous and exo, and endo and non-spontaneous for the most part.
Yes. Okay. Cool. Um, you have a picture over your face.
I have a picture over my face.
Yeah, you've got the picture of your family is superimposed over your.
That's funny.
Yeah,
It's not on my
it's a
son.
great picture.
It is a good picture. He's hilarious.
Um, cool. Okay. This cracking. So I was a little bit confused. No, I'm totally confused about how you can have molecules with the same molecular formula but different chemical structures.
Sure.
So how is that like measured and determined and
So this is rubbing alcohol.
okay?
This is not.
Okay.
This formula is C3H8O. This formula is C3H8O. Same formula, not the same
Mm-hmm.
thing. They're very similar to each other, but they're not the same thing. One catches
Yeah.
on fire a little bit sooner than the other one. One's a little bit more chemically reactive than the other one, but they're definitely different substances. So, because this usually happens with carbon molecules, because the carbon molecules bond easily and bond 4 times, I can move stuff around on the molecule and get different molecules or slightly different molecules. But this is the easiest one to talk about: propane,
Okay.
propanol, and or 1 propanol and 2 propanol. But I'll give you the example. I can't remember if they gave this in the book, but they probably did. Um, so there are 8 carbons here, and so I'm not going to draw them, but at the end of these lines that I'm drawing, these are all hydrogens. So this would be octane. 8 meaning, or oct meaning 8, so that's how we get that 8 carbons in this molecule. So what's this used for?
Octane,
Yeah,
gasoline.
yeah, except it's not. it's a crack. This is actually a really bad fuel. So what we've done.
So how does that happen?
Just a sec. Let me throw all these carbons, hydrogens up here. So both of these molecules are both C8H18. Okay?
Okay.
This one up here is octane, and this one down here, the non-chemical name for this is isooctane.
Mm-hmm.
This is the molecule, this one's the one you buy. That's the one that goes in your car.
Okay.
The reason is because that molecule burns, it's the temperature at which it starts to burn is at a higher temperature.
Mm-hmm.
And the one that's in a long straight line, it burns at a lower temperature. And if you started your car and let it run for a while, would you ever touch the motor?
Mm-hmm.
Why not?
Because it's hot.
Because it's hot. So, do you know when the gasoline is supposed to explode inside of your car?
No idea.
There's something called a spark plug.
Okay.
And when the spark plug sparks, that's when the gasoline is supposed to ignite. Okay?
Okay.
And your car is only expecting the gasoline to ignite when the spark plug sparks. If you put this gasoline in your car, the straight octane, it might explode too soon, which would do bad things to your motor, like could break your motor.
Mm-hmm.
So what chemists have done is they've taken this molecule and just turned it into this molecule through a process called cracking.
Mm-hmm.
So what they've done is they've taken a molecule that's C8H18, rearranged it, and made this rearrangement make a molecule that burns at a higher temperature. So this doesn't burn until your spark plug sparks.
Okay.
So when you go and you buy regular gasoline, you can get like 87 or 89 or 92. This is the amount of isooctane that's in the gasoline. So the higher this number, the more isooctane. If it was 100, then you'd have 100% of this isooctane stuff.
Mm-hmm.
And your car would run better. If
So
it,
how do they make that happen?
the cracking,
Yeah.
they use a catalyst, a substance that will allow the molecule to disassemble, and when it comes back together, it comes back in this form. It's not 100% efficient, which is why most gasoline is sold at that 87 marker, but it's pretty efficient. I mean, 87 is pretty good for the least expensive type of gas.
Okay. And what sort of catalyst do they use? What would an example?
All the oil
Anything?
companies use a slightly different process, but it's going to be some kind of metal complex. So imagine like a metal colander,
Mm-hmm.
and the metal colander is coated with this particular type of substance, this catalyst, and you've got a lot of these colanders, basically all stacked on top of each other, and then you run the liquid through it at the correct temperature and the correct pressure, and when it touches the surface of the metal where the catalyst is, the molecule disassembles and reassembles itself and turns into this isooctane.
Oh.
It's definitely more complicated than that, but that's the gist of it. It disassembles and reassembles itself because of the specific way that the catalyst is set up. They could make it turn into another molecule by using a different catalyst. It's just this is the one that the industry has chosen to use, and we've been using it for a long time. So when you build a car motor, you're expecting the gasoline to be this stuff.
How do they, if these things react differently, how do they, and you can't actually like see, you can't see molecules, right?
Nope, you can't see them. Are you asking me how do they know this is what the shape is?
Yeah, and how do they know that it's the same elements as before if they're
Well,
combining
you
something or
only
altering it in some way?
you're only disassembling it and putting it back together. Like I'm sure you've played with Legos before. Like
Okay.
if you have a Lego structure and then you give the Lego structure to somebody else, you're going to be pretty sure that they're going to build a different structure with Legos, and you're not going to find any Lincoln Logs in there. Why? Because you didn't start with any Lincoln Logs. So you can only have what you started with. You can't change the atoms themselves. All you can do is disassemble them and reassemble them, and that's all the chemist does is disassemble and reassemble. As for how we know what the shape of the molecule is, there's fairly sophisticated pieces of equipment that will tell us exactly what the molecule is based off of its mass, its momentum, its flight time. If we shoot radiation through it, it looks a little different. If the if there's a shape that's different, that first molecule I put up there, the rubbing alcohol, where the OH group was in the middle, and then I moved it over to the end. Depending on where the OH group is, a piece of equipment will give you a different indication to let you know.
Huh.
So you know what you got, and then you run it through the machine, and it tells you something. And so now, whenever I see that result, I know that I've got this substance in it.
Hmm. Okay. Um, so is radiation then considered a catalyst?
A radiation can make a reaction happen, but it's not a catalyst because a catalyst can't be used up. It's actually an energy input. So when you're finished with a chemical reaction, for you to be called a catalyst, you must still be there. So there's a catalyst in your car, in your exhaust system, and it's the catalytic converter. So it
Mm-hmm.
never wears out. It's always just there and it'll run forever. It might get dirt, carbon stuff over the top of it, and you might need to go in and clean it, although you wouldn't be able to actually do that. So it could lose its effectiveness because it's being covered up. But the metal itself, the platinum itself, nothing's going to ever happen to it. So a catalyst is something that helps with a chemical reaction, and then when the reaction's over, it's still there.
Okay. Okay. I think I might understand that well enough to retain
No, I didn't want to pull that up. Sorry, I thought I had a video here, but I can't seem to find it of a catalyst. Is it on here? I think I put bids on here. Maybe it's on the Chem 122. Um, sure. Sort of. So, can you see this little video?
it. Mm-hmm.
So there's this hexagon and pentagon connected to each other.
Mm-hmm.
This is table sugar. This is sucrose. And this is the enzyme for sucrose called sucrase. So, sorry, it's showing you a process that I don't want to talk about. So we're going to wait till it gets to the part where I want to. Okay, so the sucrose here has to interact with the sucrase because sucrose itself, table sugar, is no good to your body. For it to be any useful at all, I need to break that chemical bond. So the sucrose goes in, attaches to the enzyme, it breaks the chemical bond, and now I've got a glucose and a fructose. And then what happened to that little enzyme piece?
Nothing.
Nothing. That's why it is a catalyst because when the reaction's finished, Nothing has happened to it. It's still the same substance before and after.
Okay.
So that's why radiation can't be considered a catalyst because it gets used during the course of the chemical reaction. A good example of so that gets put in a swimming pool to decontaminate it, right? Chlorine. Can you hear me?
Yeah.
So you're okay with me saying chlorine gets put in swimming pools?
Yes.
Have you ever been kicked out of an outdoor swimming pool in the afternoon so they could re-add chemicals?
Um, yes.
So I was a lifeguard for a long time, and we had to do it all the time, but it only happened on really, really bright days. So on really bright days, the ultraviolet light from the sun will break that chemical bond, and you end up with these chlorides that go off and do stuff. And now, because that got broken by the UV, that didn't go off and kill something.
Mm-hmm.
So you run through your chlorine a lot faster because the chlorine was basically consumed by the UV. And so the UV is not a catalyst because when it breaks this bond, it gets used up. If it was a catalyst, then it would go through and break the bond and then just keep going on through. But that's not the case. When it breaks the bond, it's absorbed. And now that UV wavelength has been used and is gone.
Got it. I think that's all I got.
Okay.
Do you prefer our notes? Does it make any difference to you how they come to you if they're in like a doc file or copy and pasted right into the Moodle?
Doesn't matter. This it works either way. It's totally up to you.
Okay. And then I can't log into Moodle from the like Moodle login page.
Yeah, you'll never be able to log in from the Moodle login page. You have to log in through your MyCGCC.
Okay. But I keep getting redirected to the Moodle login. Maybe that's not what I think it's like Moodle.cgcc.
Yeah, the URL would be moodle.cgcc.edu. What's
Yeah.
directing you to that?
So when I time out, I get directed to that page, and then I can't log in from there. I can only log in through CGCC.
I'm gonna have to have somebody change that. So when you what do you mean by timeout?
So if I have Moodle open for a long time,
Oh. Gotcha. Yeah, that's a mistake. It does that for me, but that's how instructors are supposed to log in. So timeout for students sent to um, instead of my CGCC. All right, I'll see if somebody can fix that.
cool. So it's not just a me thing.
Definitely not. I never thought about it because when that happens to me, if I have it left open and it times out, it sends me to that moodle.cgcc.edu page, which is how instructors log in. So I never considered it not doing the same thing for students. So I'll see if somebody can change that and redirect back to the MyCGCC page.
Great.
Yeah. Okay, well, if that's it, then I guess I'll see you Wednesday.
Wednesday.
All right.
Bye, Bethany.
All right. A meeting for all, kill, exit.